T2K is the name of a neutrino experiment hosted in Japan, but it's an international collaboration.
T2K is a collaboration of scientists that are studying neutrino oscillations in Japan.
So the T2K experiment is an experiment where we produce a beam of neutrinos, and we watch those neutrinos. So actually we're trying to measure neutrino oscillation.
Neutrinos? But what is a neutrino? In order to understand what a neutrino is, we have to take a big step back and look at how the world is built. All of matter, the sun, the earth, the air, you, plants, buildings, everything around us is made of atoms. If we look closer at an atom, we see it's made up of electrons. These are elementary particles with an electric charge of -1. They are trapped around a nucleus, which is the center of the atom. The nucleus is made up of protons with an electric charge of +1 and neutrons that have no electric charge. The protons and neutrons themselves are not elementary particles. If we look even closer at them, we see that they are made up of quarks. So, in the end, ordinary matter is made of quarks and electrons. But it's not so simple. The electron has a cousin, the neutrino, a light particle with no electric charge and very strange properties. This is the family of the lightest elementary particles. But it is even more complex than that. There are 2 other families with other quarks and other leptons, including other neutrinos. The muon neutrino, which is the cousin of the muon, and the tau neutrino, which is the cousin of the tau. There are 3 types, or flavors, of neutrinos.
Well, we study neutrinos both because they are inherently interesting, but also because then we can use them to study other things about the universe. The neutrinos oscillate, that's a flavor oscillation. And what that means is that if we create a beam of neutrinos of one flavor, we can later observe a different flavor.
Here what we do is to build a beam of muon neutrinos from decays of a particle which is called pions, which can be artificially made. And then 300 kilometers away, in that muon neutrino beam, we're trying to see electron neutrinos, and in fact that's what we do see. 300 kilometers away, the beam of muon neutrinos has almost disappeared, and we see appear electron neutrinos instead.
How can we produce a beam of a given flavor of neutrinos? This is something the Japan Proton Accelerator Research Complex, or J-PARC, can provide.
For T2K program, we definitely need the huge number of neutrinos coming out of the facility. And of course, to do that, we need the high intensity proton beam. And this is the facility actually to produce lots of protons to be accelerated, to produce lots of neutrinos. That's why the T2K requires to build this kind of facility.
The J-PARC Research Center is located in Tokai, about 100 kilometers north of Tokyo. Its accelerator setup is composed of 3 main accelerators. A linear accelerator, called LINAC, a first ring, the RCS synchrotron accelerator, and the main ring, which provides beams for many J-PARC research programs. The protons used for the T2K neutrino program are extracted from this ring and bent to the Kamioka direction in order to create the neutrino beam.
We focus the protons towards the super Kamiokande direction, and then those protons slam into a long carbon target and interact with the atoms inside of the carbon, and pions, mostly pions and some other particles, fly out of the target. And then those pions are allowed to decay in a 100-meter long decay volume into mostly muons, and muon neutrinos come out. Right, so then we can easily stop the muons just by putting some rocks or dirt or whatever, but the neutrinos just travel through the Earth. So yeah, then we can have a pretty pure beam of muon neutrinos coming from our accelerator.
Neutrinos are traveling through the Earth? But then how can we possibly see them?
And that's one of the most interesting things or most weird things about neutrinos is their weak interactions with everything. So they interact very rarely with matter, so we have to make a whole bunch of them in order to study them, and we have very large detectors so that we can get a higher probability that the neutrinos actually interact. T2K experimental setup is that we are trying to look at the flavor change in our neutrino beam, and we test the neutrino beam in two places. The first is 280 meters from the proton beam target, and the second is 295 kilometers away.
The near detector is named ND280 because it's located 280 meters away from the target. It's composed of different kinds of detectors, which give many different pieces of information about the neutrino beam, which are crucial to the study. This detector was designed in order to measure the number of muon neutrinos in the beam before any oscillations occur. It's coupled with another detector, named Ingrid, to precisely control the direction of the beam. The data is collected and stored in order to compare these characteristics with the beam at Super Kamiokande. Super Kamiokande is a huge detector, 295 kilometers away from ND280, near Toyama City. It's built in a mine, 1.5 kilometers under the mountain. This is an enormous cylindrical tank, 40 meters high and 40 meters wide, filled with 50,000 tons of very pure water, and the walls are covered with 11,000 photosensors. This amount of water corresponds to 20 Olympic swimming pools. Super Kamiokande is a unique detector, but how does it work? How can neutrinos be detected in a giant water tank?
In order to measure neutrinos, you have to have something that's very heavy. You need a lot of mass, so it's 50,000 tons of water. Now, whenever you try to buy 50,000 tons of something, it's going to be expensive, even if that thing doesn't cost very much. But water is great because water is free. So we can get this target, which is very heavy, which allows us to detect where the neutrinos interact. But water is special because not only can we use it as a target, but it's actually a way to detect the particles. So how does that work? It uses something called Cherenkov radiation. Cherenkov was a physicist who worked this out in the past. And the idea is, if you think about, say, a fighter jet, which is going faster than the speed of sound in air, you know, if you're in your backyard and a fighter jet goes by going faster than the speed of sound, there's kind of a sonic boom that you hear. If you're in water and a particle is going faster than the speed of light of water, then there's something that happens like that sonic boom. It's electromagnetic sort of sonic boom, and it makes a shock wave of light, just like the sonic boom that you hear on the ground, and that light travels to the outside of the detector, and it makes a kind of a blue light, and we can see it by putting photosensors all around the detector. We can measure that light.
T2K has been running for 10 years. What did T2K already discover? And what are the next steps? What's the future of T2K?
T2K discovered a neutrino oscillation, one new type of neutrino oscillation from muon neutrino to electron neutrino.
We're very lucky. Nature was kind and gave us a very large electron neutrino appearance signal. And so now we can use that electron appearance signal as a tool to study what we call charge parity or CP violation. And that's the difference in matter and antimatter.
And in our universe, only matter remained. We don't find any antimatter in our universe now, and this is a big mystery in science. And in T2K, we want to reveal or study for that kind of antimatter asymmetry in neutrino. And that's the next big goal in T2K experiment.
And so we're focusing on that difference between matter and antimatter now, and plan to do that for another 10 years until the next generation experiment comes online, which will be called Hyper-Kamiokande.
Research on neutrinos has already given us a lot of information, but the field is still young, and thanks to the T2K experiment and all the people working in this collaboration, neutrino physics will reveal more and more about the mysterious history and structure of the universe. neutrino physics has not yet finished uncovering the hidden secrets of the world around us.